Hello, this presentation is titled The Book, Software Design Methods with Wolfram Language. My name is Anton Antonov. I'm a senior research scientist. I'm a long-time user of Wolfram Language of Mathematica. I'm a former kernel developer of Mathematica for 8 years between 2001 2008. So before going further, I would like to mention that there are 3 panels in this presentation. The one to the left is going to be with a mind map, which is going to keep us oriented where we are at in the discussion. The mind map kind of corresponds to the book. I'm going to look for questions and answer questions after each of these sections. The second panel in the middle is with the presentation itself, and the third panel is with additional materials. For example, you can look up at the current book, the way it is published. This is a paclet, in a sense, booklet. I'm trying to discuss with the Wolfram research how we can actually use the paclet system to publish books. All right, so let me go here. I cannot go through all of the slides through this presentation. I'm going to give them the most important part, which is in the beginning. The full presentation over these slides is probably like 1.5 hours. I might do it later this week or later this month, record it. You're welcome to stay after the allocated time. I plan to finish on time though. I plan to make this presentation within 30 minutes. Okay, so this book started as an offshot on an offshot. So I wanted to write a book, How to be a Data Scientist Imposter. That's actually very old at this point, especially with the large language models. Quite a lot of things changed. One of the things to facilitate for this book was to actually discuss how you do machine learning workflows. One of the easiest things to automate with machine learning is machine learning workflows, and this book here was about that. I have made multiple discussions, multiple presentations at the Wolfram Technology Conference and otherwise about using grammars and large language models or small language models to do machine learning workflows, to produce the code to facilitate machine learning. This book is Software Design Methods in Wolfram Language is basically needed for this one. Instead of discussing in these books the details about machine learning, or in the machine learning book the details about the actual facilitation, actually how we do the software design, I decided to separate them in these 3 different books. So let me see. Apologies. So the methods which I discussed in the book are object-oriented programming design patterns, monadic programming, functional parsers and grammars, and meta-programming. So object-oriented programming, I'm not sure to what degree it's important now, but I could have written this book probably like say or published it 5-6 years ago. Right now, things have changed dramatically, and I had to reevaluate how this book is going to be written, what it is, what should be in it. So I still haven't finished it. I thought I'm going to finish it by the time of this presentation, but it is there. I plan to finish it by the end of the month. So one of the things here is that we need to give a diagnosis of the current development methods. And now with the large language models, this diagnosis actually changed a lot. In order to describe why these techniques which I'm proposing, or methods I'm proposing, why in Wolfram Language, why I'm discussing them at all, we need this diagnosis. I use extensively diagrams, unified modeling language. Very interestingly, Mathematica, and not just Mathematica or Wolfram Language, but in general, quite a lot of programming right now is taught without diagrams, just from a linguistic perspective, and I don't think that's actually very didactic. And speaking of didactic examples all through that book, real life examples, absolutely, they're going to be referenced if they're not in the book itself. But I have already implemented a variety of packages using these ideas. You can see The paclets I have published, like for example, the monadic paclets, they follow, the directions in that book. And so the methods, of course, the software design methods, they're cross-language, they're valid for any kind of programming language you might want to use. I'm going to discuss this a little bit further. Probably one of the most important things is the mathematical justifications. I wanted to skip this, but right now, again, because of the large language models, it's better if we do certain bots. For example, imagine you have a bot with which you can easily apply the techniques. Like say here, the template method, whatever I'm trying to teach with the design patterns, you can actually ask a bot how to do the template methods and what exactly you want to do. And then you get the mathematical or Wolfram language code generated. That bot also understands unified modeling language diagrams. And again, it can generate the Wolfram language code. I have submitted this today, this bot. I don't think it's yet published yet into the Wolfram prompt repository. So it seems that then, saying all that, but the mathematical justifications going to be probably the most important part of this book, although I have done this already in different writings, but I wouldn't mind putting them in this book. All right, so related to what I was saying, LLMs and so forth, who is the target audience of this book? Initially, I thought that this is about Wolfram language programmers who are writing packages or frameworks, so in general, they want to have a reusable code. Most data scientists, they kind of want to do reproducible research, but they don't usually go for making frameworks. Relatively few of the data scientists making tools for data science, say, or machine learning. And so, but nevertheless, they might be in this group, but I think they're more on the casual Wolfram language group, which Wolfram language programmers who want to just strengthen their code, and they want to know certain techniques with which this can happen. Another set of potential readers of this book, non-Wolfram language programmers who want to evaluate, or they want to see, can they see some familiar methods in the Wolfram language, so in order to use it. And of course, LLMs. In some sense, it just recent realization, like in the last few days, but I'm actually writing a book for large language models. The techniques themselves, they're probably interesting, but they're not that interesting, I would say, right? If you can actually feed the content to a large language model, then you can do code generation, which I was showing, but you can also have tutoring on your own pace about the techniques or about the software design methods. So the book has been 80% completed for at least 5 years. This is the typical Pareto principle. I would say maybe not Pareto principle because it took me some time and thinking to make the core chapters of the book, but this has been done a long time ago. I started like 9 years ago to write and profess about design patterns, object-oriented design patterns in Wolfram language. The monadic programming is since 2017, I think. Currently, the book is like 97% complete. And the book itself, initially I made it with notebooks, then I wanted to do it with markdown files. Now we want to do a paclet, or a booklet, right? I'm not sure what else can it be published in other means, but I do have tools to convert from Wolfram language notebooks to markdown files and vice versa. So currently, large language models, they understand markdown best and they generate markdown best. And so again, I plan to have at least a few large language model personas about the application of those methods. So the use of large language models I already mentioned. It's for tutoring, for code generation, probably different flavors of the book versions. It's very interesting to know or to investigate, can we use large language models to derive new design patterns? It is a lot of fun to write in a bragging or dogmatic way, to be obnoxious and to tell other programmers or non-programmers or whatever how wrong they are. it's very quickly you can write some material. I'm restraining myself publishing those, of course, but there's another thing here. It's very hard to convince some people about certain methodologies, and this goes back to why I'm using mathematical justifications, or how I want to compare, Wolfram language with other programming languages. All right, so this is interesting, but actually these are questions I'm asking myself. Like, for example, can I program without large language models, or which programming languages I can program without large language models, with which I can program using LLM help, right? And which are, like, say, I completely cannot do anything without LLMs. Quite a lot of people, when they say they're programmers, they're actually not programmers, they're users, especially with Python. This is what I see. And usually the people I call users, they just learn a workflow of one or two important packages, and basically, I mean, this is how they perceive their programming activity. This can be remedied. This can be changed, right? And maybe this book is going to help. All right, so mathematical justifications. I can talk a lot about this, but roughly speaking, the object-oriented programming was considered to be a fashion of thought 20-30 years ago when I was doing my PhD. My PhD is in large-scale air pollution simulations. This meant lots of computational chemistry, computational fluid dynamics, supercomputers, and different kind of geometry kind of challenges for making the grids for the partial differential equations. So this kind of eclectic activity, doing it with object-oriented programming, I think, definitely it was a must, but it was very hard for me to convince the people I worked with why object-oriented programming at all. It's relevant, so I had to discuss it, in mathematical terms. Similarly, with monads, we can actually, in a sense, in order to discuss and have monads to do something useful, you have to use the mathematical properties. And there are some other analogies that can be made from graph theory and system dynamics. I mean, I might, I'm not going to discuss this here, but I might put it in the book. One important thing about the design patterns, object-oriented programming is very easy to get wrong, right? So it became mature with design patterns. So using relational algebra, which is from the relational databases, to prove or discuss why design patterns have to be used, it's like putting your code in a third normal form. If you look at the bodies of your functions or methods as data, and the signatures and the names of the methods or functions as keys, then you can look at your code base as a database, big database. And then design patterns, they're putting, it's like putting your database in a third normal form. If you're familiar with database theory and normal forms, they allow you to be ignorant in a very smart way. This means that you'll never restructure what you have done. And so similarly with design patterns, this is the reason they used and they're applicable. Okay, so I'm going to go for preliminary examples. Let me actually see here. I've discussed this three or four elements here in the mind map, where I'm going to move to the design patterns, but again, before moving to the examples here, I'm going to show some concrete applications. So let me see, do I have any questions here? Can you elaborate as to why OOP became more obsolete due to the arrival of LLMs? So large language models, I mean, you can see it here, right? You can see it here, how I very verbally described what I want, and this code got generated. At this point, object orientation has been written, so much material has been written about object-oriented programming and design patterns. It just take Wikipedia, or just take of the like books by Bertrand May about object-oriented software design. So these are prime sources, so to speak, for the LLMs, and they can generate code which is popular, like say Java or C++ or Python, very reliably, very well. So I use object-oriented programming every day, all the time. not with Mathematica, not with Wolfram Language, but I mean, I can see the effects. But you know, it's, from that perspective, that knowing object-oriented programming, it's more of at some point, it's going to be, first of all, it becomes less important in context of Wolfram Language, but then you can very easily change Wolfram Language into code, into object-oriented code. Now, I forgot to mention, this was very important. Thank you for this question, very important. So one of the reasons I use design patterns in Wolfram Language is not that they give me, or object-oriented program, it's not that they give me some decisive advantage. They do, but not always and just in certain cases. But very often I will make a prototype of 5, you know, of what is supposed to be done in some, you know, say some startup or, you know, some production company. And then this prototype, I don't want to be just some Mathematica code. I want to communicate it to other software engineers. I want to kind of give them the opportunity to try it out, and they definitely embrace this prototypes better if I tell them that I'm using design patterns, because they can see, you know, they immediately can figure out, oh, okay, yeah, we are just doing this in Mathematica, but with these design patterns, we can transfer it to whatever programming language of choice, Java or C++. So this was the reason for me to profess and use design patterns and object-oriented programming in Mathematica, now Wolfram Language. Now this is not that needed because of LLMs. All right, yeah, thank you for this question. This was good. So so design patterns, you can see, I want to mention here about something about design patterns, and this goes back to the obnoxious statements I was mentioning. People say, oh, when Mathematica doesn't have object orientation. It does from the very beginning, from version 1, right? So what I'm saying here, there is no package, there is no emulation of object-oriented programming. These are core abilities. This is just a coding discipline. This is core abilities of the Wolfram language from version 1, or from Mathematica version 1. So you can see how here we make this one of the basic fundamental design patterns in, you know, not just from design patterns perspective, but in object-oriented programming. It's called template method. You have an abstract class. There is some operation, say this algorithm, which depends on certain operations, which are abstract here. The algorithm is concrete here. But then you have, like, say, imagine this is some kind of matrix factorization class you have here as an algorithm. Now we have dense matrices and sparse matrices here, right? Dense matrix class, sparse matrix class, they provide their own operations for whatever, right? For dot product or whatever it is. So, so yeah, it's a fundamental pattern. You can see this is how it is implemented in the Wolfram language. This is what I'm showing you with this chatbot, right? It's basically doing, what is doing? Yeah, it's doing the template method, and I'm also showing strategy, I think. All right, so how exactly monods look like? This is actually a fun example. So let me see. I've trained, because of the LLMs, look at, say, let's look at this pipeline. So this here is a monadic pipeline. If you use monads, this means that your code, not what it is, not what it does, but the code itself has some algebraic properties. And this gives some kind of very nice convenient features for translation. If I evaluate this in place, you can see that this is an actual code which is just plugged and played here. You know, this monadic. Or I think this is going to be something more complicated or longer, right? If I try. What is happening? Yeah. Okay. So this was a longer pipeline. So monadic pipelines, they're very nice in this way, but it's very easy to use what I say small language models or large language models to produce pipelines like this. And if it is monadic, you can have some very nice features. I might expand on this. Functional parsers, you can see here, this is a parser made on the spot, which parses this type of phrases, numerical integration or symbolic integration. And you can see I have put this symbolic head, which actually tells me what is the type of the integration, numerical or symbolic, right? So you can see these operations here. It's like plus, and this is like multiplication. We can say that functional parsers, they form a monad in the space of functions which parse text. And yeah, these are the operations in that monad. So this is again, I'm not sure how popular this is nowadays. 10 years ago, it was, I would say, indispensable if you want to do anything related with parsing natural text or domain-specific languages. And functional parsers, they have been built in many languages, like say Scala. Almost any popular language is going to have at least one or two implementations of functional parsers. So this implementation here in Wolfram Language is that, which is also described in the book. All right, so so this was my examples here. Okay, yeah, we can see grammars are just another version of if I kind of put this here. So you can see, hopefully you can see, I'm generating random sentences every time I press this. So from this Backus-Nur form grammar, I'm generating the corresponding sentences. So grammars, they're natural extension. If you have functional parsers, natural extension to have grammars for them, and from grammars to generate the parsers. So there's an interrelationship between this methods, software methods. Grammars, they're used in the so-called interpreter design pattern, which is part of the original set of design patterns. The original set of design patterns is like 23. The first conference about design patterns happened in Arlington Park, which is like, say, maybe 20 to 40 miles within radius of 20-40 miles from the Wolfram Research Headquarters in Urbana-Champaign. So it started in Urbana-Champaign. Two of the authors of design patterns, I think, they were in the University of Urbana-Champaign. So monadic programming is, it can be seen as the command design pattern. As I said, functional parsers were a type of monadic programming. And there's obviously with grammars I mentioned already, we can have, you can interpret grammars. You can generate functional parsers using grammars. All right. So let me see where we are at here. I have 8 more minutes. So I'm probably going to speed up through some of this, for the rest of the slides. So the typical development process, I'm not going to expand too much on this, but let me actually see. So with object-oriented programming, so the initial idea was that we have objects, right? And these objects, they exchange messages, and this is how we program. So you can say, if you look at philosophically at this, is that in order to, your physical reality has objects, and the order between them, relative or absolute, gives you idea of space. The order of events between them gives you the idea of time. And you basically make a language which assigns, say, nouns for the objects and verbs for the processes. I mean, I'm oversimplifying here, but the question, why I'm giving this analogy at all? So the object-oriented programming was considered to be no brainer in a sense, but you have objects which exchange messages. That's why the first language, like say Smalltalk, it was Smalltalk between objects. It was object-oriented, not class-oriented. Right now, many of the object-oriented languages, they're actually class-oriented. Okay, it is very easy with the classical object-oriented paradigm to make wrong designs. So that's why design patterns, as I said, they brought this into maturity. Again, I'm emulating object-oriented program. I'm not emulating, but the way I'm doing object-oriented programming in Wolfram Language is not through emulating, say at object level or class level. I'm just doing that by basically showing how the classical design patterns can be implemented, can be used with standard Wolfram Language notions of constructs, which again, they have been from version 1 in Mathematica. So I'm not going to go further through this. It is very important functional programming to be compared with object-oriented programming. So in some sense, structural programming and object-oriented programming, we're doing a top-down design. And if you do frameworks, if you develop frameworks, you might have heard the principles of leave the driving for us, which is the Greyhound principle, or the Hollywood principle, don't call us, we'll call you. This is completely the opposite with a typical, functional programming way of doing things. We start bottom up. We actually brainstorm in a sense by writing code. We relentlessly evaluate our code. We simplify. We basically find a new domain-specific language which fits the problem area, and with that domain-specific language, we write a few sentences of, for solving the concrete problems we have at hand. Again, this is very, very different with LLMs. This is going to change. LLMs can be relentless. In order to do this bottom-up, programming, you need to be some sort of obsessed with the right code. It's like you're looking at your code as some very complicated equation or formula, if you will, and you're trying to evaluate it further and simplify it, and etc. Most people don't want to do that. Quite a lot of people, they just don't want to program, right? They just want to do a few workflows. So I'm not going to go through signature analysis. That's very interesting here. And yeah, why use these methods? I already explained this in several ways. Let me see. Again, there's 4 minutes left, so I'm going to skip through some of these elements here. So I don't think we need to see. I need to see many of this. Yeah, I want to reiterate this. This is the third time I think I'm mentioning this. I don't see the point of. Let me see. Can I do this here? Right. So you can see it actually here, right? In the quite a lot of people when they make. If I say go to this. If I go to this mind map here, and hopefully this is going to be obvious. So again, it's being with classes and objects, right? I mean, I haven't re-evaluated this, but again, from everything I have seen, I'm the only one who actually discusses doing this at pattern level and not facilitating it in any other way, just using, the core functionalities in Wolfram Language. So no, what I'm doing is, what I'm proposing here is just a discipline. I think it's detrimental to actually use most of the time. It's detrimental to use to emulate object-oriented programming at object level. And here, theoretical background, I did mention it. I'm not going to go through the technical examples. Object-oriented, these design patterns, they can be found a lot in Mathematica, in Wolfram Language, right? I mean, if you have seen, say, let me see, can I evaluate this? So this here is the typical observer design pattern, also known as model view controller. And so integrate and dissolve, they do use template method, strategy builder, and so forth, right? So when I implemented, designed, implemented, documented, and integrate, I did use these design patterns. Also, the graphic functions like radial axis plot, they have been using this. All right, so I don't see any more questions, so I'm going to continue. Monadic programming, I mentioned this several times. Let me see, do I have some examples here? So I showed this example with the classifier, but you can see here how it is facilitated. I'm basically using certain commands here, like concretize or whatever, which from natural language produce these pipelines, and this pipeline here has been evaluated. And now this is Wolfram language, but absolutely the same thing can happen if you use say Python. Okay, well, this worked without any errors before. Let me see what is going to happen. Anyway, yeah, so you can see this is again monadic pipeline, but in Python, right? And so monadic programming, this is one of the biggest advantages because it has the code itself has algebraic properties. It's very easy to translate natural language specifications or other specifications into working pipelines. So this is an explanation about monadic programming. I'm going to skip many of this, whatever I was showing with grammars and parsers. I would assume this to be sufficient. One of the things I would like to kind of go before finishing the main presentation is the future plans. So I have made different LLM personas about this. And you can see, you know, like I'm actually having plans to do this for all of the elements, for all of the design patterns, which all of the design patterns, the monadic programming and the functional parsers, they're going to be supported with LLM personas, you know, the ones which I discussed in the book. And yeah, thank you for your attention. I see a few more questions, or just one. More specifically, what do you mean that we should not elaborate OOP on the object level in Wolfram language? Yeah, I mean, because if we do say, let me see, let me go back to this somewhere here, right? So yeah, when people try to emulate object-oriented programming, they see the objects, and they want to interact. They want to have some sort of network, if you will, of objects interacting to each other. Okay, that's the original paradigm, and this is how some engineers in Scandinavia saw, you know, how programming should be. If you come with some mathematical background, I don't see this to be such a good idea. And in a sense, if you try to do it, especially before association was introduced in the Wolfram language, you need to do quite a lot of stuff. I mean, look at some of the presentations or articles about object orientation in Wolfram language or Mathematica from, say, 10 years ago. They're very cumbersome. And so in a sense, you're working against the programming language itself. And this is why I'm saying that it's not useful. I don't see it useful. Yes, I have seen this class and objects and etc. I'm actually following this. No, it's not that useful. It's just an additional paclet. It's just an additional software. What I'm proposing is that, no, we use design patterns. I mean, for me, my Wolfram language implementations, I don't need object orientation, the object orientation paradigm to find a solution. Some people, they need the object-oriented paradigm to find a solution. For me, it's not that. For me, it's object-oriented paradigm or design patterns is more to organize big chunks of code. I can find my own solution, you know, just using functional programming. Again, for me, it has been object-oriented programming and design patterns have been a way to communicate prototypes and solutions made in Wolfram language to other engineers. I'm familiar with all of these links I see about objects and class and etc. It is very, as I mentioned, it's the obnoxious statements and etc. You know, it's very easy to get obnoxious when we're discussing this. It all goes back to some kind of opinionated, opinionated opinions being voiced. That's why I actually look into mathematical justifications. If you look at the mathematical justifications, why are you using this? I mean, some of this becomes much less important. Again, many of this, they become absolutely less important with large language models. It's just not needed. You know, with if you can figure out a solution with Wolfram language, say, or Lisp or whatever, right, which is functional programming, you can translate it relatively easily into other languages. All right, so I don't see any other questions. So I'm going to kind of thank you for your attention. Thank you for the questions and for your interest. So I'm, yeah.
Anton, I think there's one in the QA section. I don't believe you answered.
Okay. Oh, yeah, because there's some pop-up window which has the full form of the arrows in the monadic example. It's a good question, but it's just actually this is going to give me an excuse to go to the book itself. So if you look at, say, how the monad code generation is being programmed, how it is done. So it's just basically fold. Ultimately, right, the application of these arrows or whatever, right? You're just, I'm not sure how well is this being seen. Let me zoom in. It's we start with say let me see here, and thank you for this question. I didn't have the opportunity to talk more about monads. Monads are some of my favorite examples. If I can actually go here to say monadic programming and why we're using it and how exactly is sorry. Again, let me do somewhat here. why we use monadic programming, and this here. So a very popular pattern in mathematics, like making mathematical theories, is to take some data or to take some whatever object, like say, think about Fourier analysis and Laplace transformations. So you take that and you transform it in a certain space, and in that space you manipulate it in some way. Like this is with Fourier analysis, with say same with Laplace transform, or say Cartesian using Cartesian coordinate system to represent geometric problems and make them algebraic, solve them as algebraic problems, and then put it back into the geometry form, right? So this is a very, very popular way of doing things in mathematics. I would say almost all mathematical theories are about this kind of representations. So this is what we do with monads, right? We take whatever is our original, say, data, like what I was showing with the classifiers and whatnot, and we transform it. We put it in this monadic space, and then we manipulate what is happening there in the monadic space. So this is what is happening here with this operation here. Right, we have some way to uplift whatever it is we start with in the monad, and then we manipulate the computations there using the monadic functions. These are just functions, right? And then we have some way. It's not shown here in this formula, but we have some way to represent it back. This is exactly what this is doing, this fold. Ultimately, this is what is happening. We're just having this kind of superposition of functions. And so here, this, I think, this picture is here made with, Dali or whatever. They're supposed to kind of show you exactly this, right? So it's basically, after you have put your things into the monad, you need this bind operation, which is being also professed here. So you know how to apply these functions to whatever kind of data. And this is what this double arrow is. It's just this kind of binding operation, right? This bind MF, right? So for every monad you implement that. Then I just need to have this double right arrow. I just need to have this as a syntax to kind of to be visualized and interpreted in this way. Yeah, hopefully I answered this question. Very good question. Thank you for asking it. Yeah, okay, so I think I answered all of the questions, and thank you everyone for your attention. So good luck with the rest of the conference.